Okay, and we are live. Welcome everyone to another live science session. So it's been a couple of weeks since we got right back into actually doing live science. And yeah, we're looking forward to basically carrying off where we left off. So we're starting with Carlos today and a continuation of infrageometry, which I know is a fan favorite for many followers of on the channel. So yeah, Nick and myself will be in attendance, as well as Dugan, who might join us in a little bit. But with that, Carlos, please, yeah, tell us what's happening in Infrageometry there.
Yeah, so thanks, James. Welcome everyone back to our life science schedule. I hope that this will be again a sort of regular fixture of our channel. I wanted to just go back to basically, as you said, where we left off, but also I think with a fresh eye on some of the questions, and I hope that this is gonna start to get implemented very soon on the sort of language end, because software is getting a bit better now, like the functions are doing a bit better. So let me just share the screen and take it from there. Guess you guys can see this.
Yeah.
Yeah. All right. So you can see your faces. Right. So today I want to essentially discuss three things, time permitting, in order of priority. I'd like to settle on a definition of a tensor graph. I'll explain. I'll give you the reminders and the sort of warm up as necessary. We'll revisit the question of the directional derivative or covector pairing that was our bottleneck last time and still remains our bottleneck. But hopefully, if we spend some time thinking about the tensor, sort of tensors in general in this infrageometric setting, maybe we have some insights as to what covector pairings might be. And then, not directly related to infrageometry per se, although absolutely necessary for it in the midterm, I wanted to talk about path algebras as symmetry signatures. So this is really for the sort of backbone of the hypergraph implementation that we do. So this is the idea that we want to think about edge types and edge symmetry with these spinal graphs that are essentially just directed graphs. And so I think it'll be interesting to end with a bit more of a theoretical conversation around how to go from a directed graph to a symmetry object. I mean, typically one might think of the permutation group, but a bit more general than that. So time permitting, I'll like to use a few minutes in the end to talk about that. So let's give our diligent overview of infrageometry. So the main idea, of course, is that we want to take a hypergraph, and by hypergraph now we mean undirected, probably connected just by default, simple hypergraph as our model of space. So this will be an analog to considering a topological space, for example. But in our case, it's just a discrete combinatorial object. We don't have any more information about it. And we want to generate structure, mathematical structure, computational structure on these kinds of objects that allows us to say that we are somehow doing discrete differential geometry, or that we're somehow capturing discrete geometry, or what we like to think of as infrageometry. So I really want to stress the fundamentals again, because I mean it's a good exercise to come back and revisit this sort of research questions again and again, so that we can have a bit of a fresh pass conceptually to what we are doing at large. And I think what's really important here is, again, we are trying to take hypergraphs as the foundation for geometry. So obviously that's going to entail a few things, and some people might be familiar with the simplicial sets, and some people might be familiar with algebraic topology and techniques using simplicial complexes and things like that. But here the philosophy is much more rudimentary in a way, that we are giving a hypergraph which by default doesn't give us a ton of information. It gives us very limited combinatorial information. And the idea is to try and reconstruct as much as possible the kinds of operations or the kinds of computations that one does with familiar differential geometry. So the first thing that that one perhaps needs to think about is, okay, what does this combinatorial information mean, or how are we thinking of it conceptually to infer some meaning from it? So of course, many viewers of the channel will realize that, or will remember perhaps from previous settings, that we are identifying the nodes to be our locations, essentially. So these are the landmarks in a landscape, or some kind of base points where we can exist. And the edges essentially represent the betweenness information that we have about these locations. So if there exists an edge among a set of nodes, all that means is that in some very abstract, very disembodied sense, there exists a space between those points. So as you can imagine, this is kind of the most primitive notion that one can imagine for space, where space has many notions like directions and shapes and dimension and so on. But I guess the most discrete, simplistic, almost Boolean valued notion in space is betweenness, right? Is to say, hey, here's a bunch of points. Do you have anything between these points? Can you somehow say that somehow between these there's space or not? So that's essentially what edges represent, right? They represent this fundamental atomic betweenness information between edges. So that essentially creates a sort of a two kinds of places where one can stand. And so that's what we call places. So a place is both a node of your original spatial hypergraph or an edge of your original spatial hypergraph. So in this visualization, you can see, we have this nice function, generate some reasonable, this don't pay too much attention to the details here. This is just generating some what I call random small hypergraphs, so which is some simple and connected reasonable graph, right? So for demonstration purposes that have a few binaries, a few ternaries, and a few quaternaries, and just nicely spread out. So if you take that as your spatial graph, the places are just creating new nodes, essentially sort of hovering over the edge. And so here we just place them in an embedding that puts them in the middle of every edge. And so the idea is now you have two kinds of places that you can inhabit. The node places, or the vertex places, which are just the places where you can actually rest, so to speak. And then you have the edge places, which will be the places that you will visit in your journey between vertices, between the actual proper stable places. So this might seem like a artificial or harmless distinction, but in a way, the game of infrageometry, as I see it right now, has to be take this approach where you have a graph. By the way, I will say graph constantly. I might mean hypergraph. It will be obvious from context. By default, it will mean hypergraph. Where you have a graph and you basically imply a set of new nodes that you can treat discretely, computationally, and so on for sort of formal purposes. And the idea is that with this information, let's try to build geometry as much as possible. And why is this a good idea? Why did we decide to think of places in this way? Well, that's because in geometry, in the usual expositions of geometry, you would have notions not just as points, which is the idea that you have nodes, but you would also have some notion of proximity. If you're coming from topology, you will have a notion of open set. If you're coming from metric spaces, you will have maybe a notion of distance and balls, which effectively give you open sets. And so a notion of neighborhood and proximity and things like that. So we take an approach that actually gives us neighborhoods as a secondary notion. So neighborhoods in this approach, which is something that I didn't formulate explicitly last time, so this is a bit of new content here. Neighborhoods are defined essentially as the relationships between all the nodes that are shared. Sorry, all the edge places that are shared in a single vertex space. So it should be very clear to see with examples, right? So here's our hypergraph, and I have this little widget, the neighborhood edge visualization. And I take that node over there, and what I do is I create an edge that is again undirected for simplicity and highlighted in red, that that binds the two the two edges that are incident on that vertex, right? So if I keep moving around, you'll see, for example, here, same idea, right? I have two edge places, and so this neighborhood is simply the edge that exists on those. Can move around, and so for example here there's only one incident edge on that, so the neighborhood will just be that edge. So neighborhood edges will always be of the form one vertex node and then n or many edge nodes, right, or edge places. So they always will have this sort of pointed edge structure. If we decide to make them undirected, they will still be somehow typed in that way, which are like pointed, like a pointed set where you have a collection of things, or a pointed bag where you have a collection of things, but one is pointed, one is singled out, right? And that's because these are essentially based sets. These have a base point, and like open balls are. So this is our effective notion of open ball. So for example, if you go here, this set over here is just, this node has three edges incident on it. So this would be a quaternary edge that has three black nodes and one blue node, and so on. I think this is pretty clear. So any comments or questions on the definition of neighborhood? Because this was never explicitly spelled out before, but I think it's important for the definition that's coming.
You mentioned a word there, edge. So you said it's a one vertex node to many edge nodes. Is that the correct terminology?
That's right.
Yeah. Not
right.
edge places or places.
Well, yeah. I'm jumping with the terminology a little. So,
okay.
So just to emphasize the fact that these things are nodes in some graph in our construction, I'm calling them vertex nodes and edge nodes. And, there's a convenience that vertex and node are different words and essentially synonymous in this. But these are edge places and vertex places. So in the general
parlance, so would it be correct to also reword it as every vertex node has many places that constitute its neighborhood?
Correct. Yes. Okay. That's exactly what the neighborhood is. So it's a collection. So no structure, no internal ordering, no orientation. But it does remember that it's based on a vertex place, right? It does remember that. So visually it's clear that there's a blue one and there are several black ones. That's obvious. But more formally, you should be thinking of an open ball. This is an open ball. So one comment I can make about neighborhoods already at this level is that a neighborhood in a way is connecting what is otherwise unconnected. So if actually let me see if I can illustrate this with so my favorite example to discuss these things, which is just the triangle. If this were a spatial graph, this will have a single edge place, right? There'll be three vertex places and one edge place here in the center. So the idea is that any neighborhood for 1, 2, and 3 will look like just this kind of thing. This will be, oops, that's going to be drag it, and I'll create. Okay. Oh, we decided to crash. Okay. So yeah, I don't know why. but let me make the point. You for every vertex place here, your edge, your neighborhood will just be a line, right? So here we'll just have a single your incident structure. Let's get rid of this, and let's get rid of this, and let's just rerun this. So in principle, that's because you have a single. So think of this situation, right? I'm not going to draw it again just for safety. So in this edge over here, I have a single edge place over there, right? So the incident structure for this node, for example, if there was no other hypergraph but that edge, will be a single line, right? It will just be one pairwise edge. And so what I find interesting is that, if you know that you can go from 1 to 3, I really want to have this model. Shouldn't crash this time. At least I'll just draw the triangle. Okay, can I do this? Apparently not. Okay, so drawing a second edge somehow crashes it systematically. But yeah, so my point is the edge so having a ternary edge is a single between a statement. If you have a ternary edge and a binary edge, which is what I was trying to draw, then you have two between the statements. And therefore, you can say, that between 2 and 3, there's two different ways that you can travel, right? Oh,
that's me.
Do that.
Yeah.
Thanks. Yeah. That was, it coincided with the updating of the text. That's funny. Really play a trick on my brain. All right, thanks so much for that. That's some live fixing. Right. So okay, thanks for that. So yeah, if I have this kind of situation, then suddenly between 2 and 3, I have two between the statements. I have the ternary edge between the statement, and I have the binary edge between the statement, and therefore you can claim that the space between 2 and 3 is larger, right? And so if you are looking out from 3 into the vastness of your hypergraph, right, you see, like, immediately you see a space that is larger than if you're looking out from 1, right? So that's why I wanted to draw this picture. Like, it's a very small picture, it's a very silly point, but it really sort of, I think, drives home this notion that of why we're defining neighborhoods in this particular way. Now I just have to scroll down. And so that's basically the idea. Right? Like, the idea is what you see from your single from a vertex locally is what defines your neighborhood, which should be exactly intuitive, right? That should be what a neighborhood is, right? Now, this is what we should use to construct the infinitesimal notions in our space, right? So our space is really the set of points, right? And the connectivity between points defines the infinitesimal structure of our space, right? And infinitesimal structure means, the best intuitive way to think about it is, I can, as an agent, I can be in space, and, you are whatever you are, that's your state. And I can also have an intention or where to go in my space. So having an intention on where to go in my space doesn't change where I am, but it will change as long as, time moves forward or something. So that idea of intention or like aiming for a direction is what the infinitesimal structure gives us, and that's exactly what the tangent graph is meant to capture. So let me skip charts for a second, and we might come back to that maybe in a later session, because today I think we're going to be a bit tight. So the tangent graph is it captures exactly this notion, right? So we, first of all, we create the pairwise graph of all possible walks, essentially, that can be traveled in our hypergraph, right? So this is just a good old bipartite graph where you have blue and red, so blue and black nodes, so edge places and vertex places, and essentially what this is the line graph of the hypergraph, right? I mean, there's just another way of saying line graph of your hypergraph. But why it's interesting is that you can now think, okay, so there's a notion that wouldn't be so obvious how to capture in a hypergraph in general, which is a notion of a path, that now becomes much more clear. Which, if your hypergraph became a regular graph, a regular pairwise graph, then paths are obvious. And so you take the notion of shortest distance path, and that should give us the infrageometric analog of tangent vectors, right? Or infinitesimal paths, infinitesimal displacements in your graph, in your space. So an infinitesimal displacement in your space basically means you point to a edge place, from a vertex place to an edge place. That's what an infinitesimal displacement should mean. And I think it's really cool that we have this idea of edge places and vertex places to capture this, because if we were doing the naive approach to infrageometry that we had last time, a few months ago, we wouldn't really be able to make much progress, because suddenly the smallest displacement is already a whole displacement, right? So that idea of sort of that the geometry revolves so much around, which is this notion of infinitesimal and sort of going in sort of small step, and then you make it whole. Small means differentiation, make it whole means integration, right? This kind of idea, we didn't really have a lever to pull there. We didn't have a real fulcrum to be able to articulate that sort of notion. Now we do, and might well be that this is too simplistic, that we might need a more refined notion of infinitesimals, meaning that there might be different depths of edge places. So we might have the essentially within edges, one might have subgraphs that are all made of edge places, right? And but are nonetheless full hypergraphs. I mean, that's a possibility that we have to keep in mind. But for now, it seems obvious to just simplify that and say, well, let's just have one trivial graph there, which is a single node, and work with that and see how far we can get. So we can get some distance already, because the notion of a tangent vector again becomes fairly obvious. So now a tangent vector is just a directed edge that goes from a vertex place to an edge place. It's clear enough. So this whole thing is what we could call the tangent graph of our spatial graph, which just shows all the possible directed edges between edge places and vertex places. And now we can superimpose it so that it looks even more intuitive, right? So here it's quite obvious that if I have a ternary edge here, so my space between these 3 points is represented by this single edge place, then it's clear that I can go back and forth there. I can go back and forth there. I can go back and forth there. And so this directed graph, the paths on this directed graph will generate all the possible paths in your hypergraph, right? So as a directed graph, this contains all the possible. This contains or in this information, you actually encapsulate all the possible paths that you can have in your hypergraph. So it's a neat encapsulation of that. And so the analogy here with traditional differential geometry is full, because in the same way that one can think of, the space of all possible paths in a manifold, right, in a topological space, is wild, right? When you think about it, that's all the possible squiggles that you can draw on your thing, right? So it's this vast, infinite dimensional thing, really wild and vast. However, we know that if we instead of thinking of the literal set of all paths, we concentrate on the structure that give us infinitesimally at every point the ingredients to cook up a path. If we were to integrate it, then we can actually capture all that space in a much smaller object. And that smaller object is what's called the tangent bundle, right? Which is just the union, so the collection of all tangent spaces at every point. And the tangent space at every point is basically all the possible velocities you could have at every point of your space, right? So that's the full analogy here. The full analogy is in a hypergraph, once you define your edge places, there's a well-defined notion of path. And, there are infinitely many paths indeed in a hypergraph, because there's no limits on whether you can backtrack or you can revisit your nodes or anything like that. So indeed, your set of paths is infinite. It has infinitely many elements, even starting from a finite hypergraph. However, your tangent graph that contains the information to generate these simply by performing iterated compositions. So you can think that, if you have a path, I think I have a nice representation here, right? So if you take this and you think of this path here, right? You can imagine that all it takes me to do is to compose this with this with this with this, to the point where I get a path from 12 to 8 in a direct way, right? So the information of this path, for example, is contained in the whole tangent graph already, right? So you still have to generate it, you still have to specify the information to pick out a path, but you don't have to construct anything new. It's already there in its building blocks, right? So I think I would emphasize this again today, because to me it seems that the tangent graph is a really nice analog of the tangent bundle, and it's one case of a tensor tangent bundle that is very natural and obvious. And the whole problem that we have now, which is defining other tensor bundles and covectors in particular, and how the pairing between vectors and covectors works, and therefore how the directional derivatives work, and so on, so it should give us some guidance, right? So the tangent bundle should give us, the tangent bundle examples should give us some guidance on how to do this. So yeah, the analogy is cool. What in differential geometry, one likes to keep things finite dimensional. So cardinalities are always infinite, because if you're doing things over real numbers or complex numbers, then your whole thing is always infinite cardinality in terms of sets. But geometrically, you like constructions that that are so that when you begin with finite dimensional objects, whatever definitions you end up with give you finite dimensional objects. And this is very much the case of the tangent bundle. And I'll say it again for pedagogy. So in the case of the tangent bundle, when you think of a space, the set of all possible paths between any pair of points or around a single point is not only infinite in size, but infinite dimensional, if one were to try and chart it with geometric charts. However, if instead of having the literal space of paths, one restricted to the space of generators of paths, so the bundle whose sections will be the vector fields that integrate paths locally, then one retains the finite dimensionality. And all you have is essentially the tangent bundle, which in a sense is just a boring extension of the manifold itself, because it's just, if your manifold is n-dimensional, your tangent bundle is 2 n-dimensional, all you're doing is putting a little vector space at every point of your manifold. So that's exactly why we like the construction of the tangent graph, why we think is very natural. It has the nice property that the spaces of tangent vectors, so to speak, so the directed edges from a vertex place to an edge place are disjoint. So this is another nice analogy, right? If I take, I don't think I have the visualization here. So if I take any vectors here, right? So from this, I can illustrate it with a neighborhood, right? So if I have a neighborhood, say, no, I have to run this again. So what I'm trying to say is, if you have a neighborhood, say from this vertex place, the tangent vectors coming out of this one will go into this one and into this one, right? So that's a set of directed edges that does not intersect the set of directed edges that will come out of this one, or that will come out of this one, or that will come out of this one. So again, we have the nice analogy that are sets of edges, sets of purported tangent vectors or discrete tangent vectors at each base point, at each vertex place, are disjoint from each other, which is also the case in differential geometry, right? The tangent spaces are formally distinct, so they don't share elements. They don't have vectors in common, right? Because they are always their tails are always based at different points. So there's another nice analogy there, and of course there's the
that's a function of the space being Hausdorff.
You mean in the differential geometry case, or
no, topologically? I guess well, I mean, so you have like a neighborhood, you have 2 points, and you can separate them by discrete non-intersecting neighborhoods.
Right. So in the context of geometry, yes, that we need that separability for the construction. But even in classical differential geometry, we don't, like, the definition. The point I'm trying to make is more pedestrian in a sense that you just have vectors track their base points, right? So in your affine space definition, you can say that a vector is only equal once the tail point and the arrow point are the same, right? So under that definition, you know that even in classical geometry, in classical differential geometry, you will have the disjointness of tangent spaces. Even when tangent spaces are subspaces of your ambient space, right? So this is the point I'm making here, that even in a very pedestrian way, and something that doesn't seem very relevant, but it is certainly an analog and a nice correspondence here, which is that I can assign to each vertex place a single disjoint set of tangent vectors at that vertex place, right? So the final good analogy that I wanted to point out, and what to me sells the concept and sells the definition of a tangent graph as the correct one, is the fact that there is a notion of integration of a path, right? So just to give some context to people who might not be so familiar with the differential geometry picture, remember that I said that one can capture the notion of a path in this infinitesimal object called the tangent bundle, or the tangent spaces in the points of your manifold. So if you give me a field, as we call it in mathematics, a distribution of tangent vectors, which is what people usually call a vector field, that is smoothly distributed and smeared in a smooth way, then it should always be possible to kind of follow where the directions are pointing. That's the point of it being smooth, so it doesn't scramble and do some chaotic thing. You might always be able to say, hey, I am at this point, so the arrow is pointing in this direction, so I'm going to walk in that direction. But then you displace a little bit, then there's a new arrow pointing in some other direction, so you update and you kind of continue walking sort of with the flow of the field. So that notion in continuous geometry is extremely powerful. It's sort of one of the central constructions in the whole of differential geometry, and now we have it here as well. So here, what we have is you can specify a path in terms of just a succession. Let me say, if you have a distribution of tangent edges, so basically directed edges between edge place and the vertex place. So in this particular case, we can see them like this one, this one, this one, this one, this one, right? That particular distribution of edges will make it so that you have a path that goes from 12 to 8. So you can integrate it at different levels of granularity if you like. I mean, this is something that in the continuous case, because everything is continuous, everything is squished down to the infinity smoothness, right? Or the kth smoothness case, and so you get a single path out of your integration. In the discrete case, we don't have that because we are always finite, so you always have some finite resolution, and therefore you can choose at what level of the resolution you are. But in at any level of resolution, this particular distribution of arrows in your graph will be integrable, right? And so it will integrate to paths. I mean, obviously, if I give you a different distribution, which is just like subscatter of arrows in general, it will not be integrable, right? So anyway, that's the summary of why this notion of tangent graph, in my view, really give us the model of what a tangent tensor bundle should be like. And that's a bit like in differential geometry. Usually one defines the tangent bundle first, or the tangent space first, and then sort of works through the other objects and how the other objects relate to the tangent bundle. So anyway, any comments or any questions? That because the idea for this section of this live stream is I want to hear your thoughts and maybe brainstorm a little on. I mean, I will present you an idea of how to define general tensor graphs, what I'm calling tensor graphs, which is generalizing vectors to multivectors and covectors and forms and all that. But before we move on, I think it's good to sort of circle back a little bit and see what you guys are thinking about this tangent graphs.
Well, it's interesting because usually with manifolds, you would start with a base sort of neighborhood model and say, okay, you have all these neighborhoods that are the same. They're diffeomorphic to a little piece of Rn for some fixed n. That you have, like if you want a two-dimensional manifold, and you have like little two-dimensional neighborhoods that you stitch together, and the thing glues up and becomes a manifold with whatever topology that is dictated in the atlas. Here, this is a generalization where the neighborhoods are not isomorphic or diffeomorphic.
Correct.
I guess some thoughts about thinking about paths in a space. The way that's usually set up is you take a linear a section of the real line, let's say, and you say, okay, I want to map that into the space in a continuous way, and just so long you have a one parameter family of points on the line, in the same way you have a one parameter family of points in the space, and it makes a path. So it'd be interesting to look at what it means to take a discretized piece of the line, let's say a section of the natural numbers with where each, the connectivity of a linear graph of nodes, a finite length of piece of natural numbers, and then say, okay, we have a map of that thing onto our graph, and what is the notion of, let's say, the tangent space of that piece of the natural numbers, and how does that map into the tangent space of an arbitrary graph? Those are some thoughts that I've been having.
Yeah. So some couple of follow-ups where you said, I think it's quite interesting. So on the one hand, yes, the neighborhoods are now not diffeomorphic or homeomorphic or your favorite notion of isomorphism to some model space. And this is something that we might want to explore at some point, where we are thinking of model spaces. And this is why I wanted to skip over charts. I mean, charts is very schematic here. But when you have, imagine that you have these two spatial graphs, which are the same base spatial graph, but you're somehow highlighting two subgraphs, so effectively two sub-chunks of space, right? And they overlap in this sort of magenta region over here, right? And so the idea is that whatever, because I will explain later on that the whole philosophy here is not to do maths on these objects, not to actually run the usual mathematical machinery where you would take these objects and kind of put them into a set and then define an operation in that set, and then maybe you also belong to a category, and then you study the category. It's like we really are not intending to do conventional maths with these objects. We are trying to perform the analog of what we think the maths should be, but at this discrete computational level. So that's going to be rewriting. And so the notion of charts, I think, kind of is somehow recounted or recovered in a way by specifying the domain of rewriting. And this will be maybe clearer in a bit when I recount this idea of rewriting. But that's the comment on the neighborhoods. Your second point, I forget for a second. You said
paths and modeling a linear graph.
Oh, yes. So exactly. So even to also to this point, when you think of a path as a mapping from an interval to space, that you want to ascribe some kind of continuity or smoothness or whatever condition to the mapping. Of course, one could think, okay, all you're gonna do is, that's in fact why I kind of put this outside here. It's like you're gonna have some model path that goes, like blue, black, blue, black, blue, black, in this way, and then you have to map it onto your actual hypergraph with a graph embedding, right? With an injective graph map. So that's perfectly fine as a mathematical definition of what's happening. But as you'll see in a couple of minutes, I hope, that's something that one can do once you have these objects, but I'm not expecting it to be the foundation of the definition that we use in practice, right? And so maybe let me just move on to that, because I think it will make a lot of sense. So what is the philosophy here? So the philosophy is that we really want to be just using hypergraphs and rewrite rules of hypergraphs, right? Like we want to be as parsimonious as possible. We, of course, we might need to put some, architecture around these things. It's not that these things are going to magically generate everything we want. We're gonna really put this on rails, and they're gonna do whatever we want them to do. And so effectively, we're just going to be replacing mathematical objects or conventional mathematical objects with maybe this hypergraph rewriting objects, or these sort of, as Stephen might like to call them, infra calculus objects or infrageometric objects. So the idea is that we don't teach our objects what to do at all. Like we don't tell them, hey, you're in a set, and now I want to do this construction, and now because you are in this set under this definition, that's where you're going to be. More than doing that, we're gonna take basic computational processes on these objects, which basically to us means defining some rewrite rules that are going to apply in this multi-way system fashion, and we're gonna try to extract from those computation streams, or from those cascades of causal events. We're gonna try and extract different metrics or different properties or different facts that then we will understand as the mathematics of these objects. So let me explain what I mean by that. So for example, one can essentially count the density of these hypergraphs, right? So I said that you would ideally want your space to be represented by a simple connected hypergraph, but if you relax the simple part, then you can begin to imagine having essentially what amounts to be integer counts at every place, right? Both vertex and edge, right? Because if you have unary edges, that gives you sort of the counts at the vertex, and you have nary edges in general, that will give you a count on that vertex place, right? So that essentially gives you a sort of a pure hypergraph notion of density or function, right? So without having to define something like, oh yeah, choose your favorite field, or rationals or naturals or booleans or reals or whatever, and map all your objects in your hypergraph to that. That would be a natural construction to do, and that's something that can definitely be done. But instead of doing that, we say, no, no, no. We don't assume anything else. We just have more hypergraph stuff, and we simply measure, say, the density of those things, right? So in this very simplistic case of multiplicity counts, we take the hypergraph as a whole, and we just register the multiplicity counts. Here, the point is that you can get multiplicity counts by applying a rewrite rule, right? And the rewrite rule is basically just reducing the multiplicity, right? So it goes from 2 unitaries to 1 unitary, 2 binaries to 1 binary, and so on. So we can similarly generate stuff with this thing. But most importantly, the algebra of functions that one gets in geometry.
How does making the reduction return the number of multiplicity, let's say?
So that the number is contained in the causal structure of the rewrite system, right? So
that's like how many times did it have to reduce before it got down to reduce the state, I guess.
Exactly.
So if it had multiplicity 3 and you reduce it twice, then you know.
They're called normal form. Or...
Exactly. So it's a localized. So for this particular example to make sense, and this is what I meant earlier, that we will use rewrite systems, but we will put them on Rails to do the work that we want them to do. In this particular case, you get multiplicity counts exactly by saying, hey, these are the allowed rules, which go from 2 edges to a single edge, right, on a minimal number of nodes. And you apply it, edge-wise. So you go around your hypergraph and you say, hey, I'm going to place myself on this particular vertex, and so this is what I meant by this chart idea, that you will actually declare where locally you're applying your rewrite rule, and where you're doing your maths, so to speak. And so when you refine enough to just be exactly at an edge or an edge place, so in this case, just a collection of nodes that contain the edges of interest, then you know that according to these rules, your causal graphs are going to be just path graphs, right? They're just going to be chains of rule applications. So you can just take the length of that chain, and that's the multiplicity at that point, right? So it's just a simple example. I'm not ascribing to it that much meaning, because in a way it doesn't seem to be that fundamental or useful, but it does illustrate that simply with it's very pedestrian, it's very elementary, but it does illustrate that you can get typical information that one might induce by hand, or be tempted to just say, hey, our functions are going to be just weightings of our places, right? Like we're just going to scatter some numerical values around our vertex places and our edge places. Well, sure, that is reasonable, but the whole point is that we don't have to do that if we have rewriting and this notion of locality and local application of rules. We can get the same notion just as easily, right? And that allows us to be very parsimonious and still say, hey, everything's going to be rewrite rules. So let me talk about another rewrite rule I think is much more clarifying, which is path integration, right? And that's what we talked about already. Like if you have this particular structure, in fact, this probably will have to be typed, right? You have to have a vertex place to an edge place to a or maybe not, because if you're actually no, you wouldn't need to, because your path graph is already well formed, and if you integrate paths there, you get an actual path regardless of the nature of the vertices. So I hope it's clear that if I take this rule over here, and I'll just copy for visual clarity, and I'll bring it over here, right? I think it's quite obvious that in different steps of the rewrite, I'm going to get these kinds of things, right? At first, I'll integrate, and this longer path, I'll compose that with that, and I'll get that line. So you get this line, 12 to 15. I'll compose this with this, and you'll get that line, and you get, 15 to 9, and so on. And that's, again, if you want to refine and just get these intermediate states, you will have to be careful about which, vertex place or edge place you're integrating. But in the end integration, the whole path integration, so the confluent state that you get here in your terminal rewrite state, you will get the total path, like the 12 to 8, and you know, there are no more arrows to compose here, right? Like you can't go further, you can't continue rewriting this. So that to me is a pretty powerful set of examples, right? Like by the way, I didn't mention about this local algebra. So the functions give you a local algebra in conventional geometry, in continuous geometry, right? Where you can, just by virtue of being valued on a numerical set, you can pointwise add, pointwise multiply, and so on. You can always do these pointwise operations. The question is, how do we recover that in terms of rewriting? Well, again, it's all a matter of setting up the rule in an appropriate way and keeping with this local philosophy, this local application. So in this case, actually, it doesn't matter whether it's local or not, because the rule is already constraining to be local, because it only will match to local stuff. And so basically, what this means is, you know, if you have two hypergraphs and you label them X and Y, and these are two different hypergraphs on potentially the distinct set of nodes, but there might be some intersection, otherwise you won't be able to, you know, they won't talk to each other at all. But if these two hypergraphs exist on each other and they are labeled because you know they're distinct, that's why we're saying we have two, then you might have a rewrite rule that says, you know, take any edge you find with any labeling, X or Y, and relabel it X plus Y, right? So that basically will scan the entire the entire possibilities and will just call everything the same label. So that would effectively just do a hypergraph union of the
vertices.
Of the edges. So this happens.
What are you talking about? The addition operator that you were trying to define, or the multiplication?
Addition. So the way this works, and this we have implemented actually. So, you know, we have this kind of thing, right? In 1, 2, 3, 4, 5, and this addition is this primitive. It's essentially a additive union operation, right? Where if you have
the vertices stay the same, you have two sets of edges defined on the same vertex set, and you're unioning, you're adding them together, basically. So not
necessarily the same set of vertices, potentially overlapping.
Right, overlapping. Yeah, potentially overlapping.
I mean, if they don't overlap, then you just have two disconnected halves. It's not there. But if,
I guess trivially you could call one, if one side has vertices and the other one doesn't, then you can just kind of add those vertices to the left and say that it doesn't have any connectivity edges on defined on those. But in any case, so you're taking basically a union of the vertices and a disjoint union of the edges.
Yeah.
Okay.
Or multi-set union in general. Yeah.
Right.
Yeah. So that's addition. Multiplication is similar, where you're basically just sort of multiplying the multiplicities, right? In the exact same way. But the point is that these constructions are natural, right? Like these are just the typical, you know, if you had your, an easy way to see this is if you take your adjacency matrices of these graphs, right? Or adjacency tensors or hypermatrices, or we'll call them, but just for simplicity, I'll use matrix and graph, just ease of language. If you take the adjacency matrices of these things, it's clear that you can do direct sums of matrices, and it's clear that you can do Hadamard product of matrices, right? So these things are defined wherever the matrices overlap in indices, right? So you can always rearrange them and put them in sort of in the right block form, so that, you know, the indices that actually align with each other are just form a sub block, and the others are just off diagonal blocks, right? So the two operations that we're talking about here is literal matrix addition and literal Hadamard product, right? It just so happens that, you know, we have this freedom to have, you know, floating vertices that are not shared. So these are perfectly well-defined operations when, in any case, disjoint vertex set, partially overlapping vertex sets, or same vertex set, right?
There's a way potentially to do subtraction as well, which would be quite interesting because that's a bit more of a complicated case. It's not just the inverse of addition.
So, well, subtraction. I mean, we are in a semi-ring, right? So in principle, like that's sort of the baseline assumption here. Like doing subtraction fully. I mean, you can do subtraction in some cases. It's obvious that you can do that. But it's basically the same idea. You stumble upon the same issue as doing subtraction in general for natural numbers. It's like it's
complicated. Yeah.
I mean, I don't think it's complicated.
If you try to do it based on like Peano axioms, it's like it's not as easy as successor functions. On like to do subtraction, you have to create this like like a you have to yes, you can do several things, but you essentially have to define the classes of solutions to equations that don't have solutions in your naturals and so on. Like you can do it several ways. Effectively, you have to invent negative numbers, I mean, I think it's perfectly okay to invent negative hypergraphs in this sense. Like it could just be a disconnected graph after the binary operation. The part that is still disconnected could be negatives. Could be the negative.
Not quite, because the connectedness doesn't really have anything to do with the positivity of the operation, because your operation doesn't really care about connectivity. Addition and multiplication are completely independent from connectivity. They don't see connectivity because they are local operations. Like they only match exactly where each edge sees only the edges that are incident on the same set of nodes, right? So the operation is not doing any kind of convolution around the hypergraph. So
yeah, not necessarily. I think the thing is, like, if you do subtraction, the thing that makes it kind of unique to addition, and I might be wrong, but you can correct me, is that you can go past zero, which is kind of the issue. Like in addition, you can only go upwards, but with subtraction, once you get to zero, then you can actually keep going. You can have like negative edges theoretically. So what I was saying, instead of having a negative edge, you just make that an edge on a disconnected graph. That was kind of an idea.
Yeah. I mean, sure.
I mean, there's subtraction. There's a set complement of edges.
Yes. So you can the idea of putting it in somehow in some disconnected set of nodes. What I was trying to say is that just putting it in a disconnected set of nodes is not enough, because once you take that as part of your hypergraph, there's just more stuff in the hypergraph. So it's more positive multiplicity in there. You have to somehow specify, no, actually you have to weight those with negative multiplicity, because if you were to perform any operations on them, they would add. They won't be negative, right? Like you want them to have the property that when you add that to something positive, it gets you of the same magnitude, it gives you zero again. And it won't have that property just by virtue of being disconnected, right? It will just be, So the intuition is right that you need to somehow have a different category or class of graphs, but that is accomplished by just labeling. And you just label them as negative. I don't think that's very mysterious. I mean, we are already having to use labels to instruct how our hypergraphs are operating with each other. So it's perfectly fine to say, well, take this hypergraph to be weighted by this negative label, right? And so effectively, that's just given some integer labels to your edges. But anyway, the point of all this, not to get too derailed with the operations of hypergraphs themselves, is that you can perform both addition and multiplication entirely locally with these two rewrite rules, right? So I think it's quite obvious that, I mean, assuming that you have your hypergraphs by default in your sort of disjoint union operation by virtue that you're considering them together in a way, they're ready for computation, then all you do is you say, wait, well, if you have any label, relabel that as plus, that'll just be basically do nothing. So that's why it corresponds to additive union. And in multiplication, it's quite interesting, because all you do is you say, whenever you see two edges with two different labels, then you write a new one that is labeled x times y. And you might be thinking, this seems that multiplication is reductive. So how am I going to get, that I multiply the multiplicities? That's how multiplication should work. And that's because of how rewriting works, right? So this is a pattern that will match on the left-hand side. So this will scan for all the possible X and Y pairs in any given edge place, right? So if I have 2 X's and 3 Y's, right? For each one X, it will match 3 times the Y's. So it will have 3 outputs out here for each X. So if I have 2 X's, I will have a total of 6 outputs by application of this rewrite rule locally on that site. So 2 times 3 equals 6. So that's exactly what you want. You want that locally you have this multiplicity being preserved, right? So anyway, so these 3 examples to me show that if we wanted to, we effectively have our usual differential geometry or local geometry constructions purely in terms of hypergraph rewriting. Right? It is still unclear to me exactly how, if there's a connection between this and a approximate version of differential geometry, meaning that if I take a discrete model like this, I can somehow blow it up to some statistical limit, and then I get some sort of smooth out version of discrete geometry. These things are still unclear to me, but what it's very obvious to me is that from a formal point of view, if you believe that the tangent graph is a good analog of the tangent bundle, and you believe that multiplicities of edges are a good analog to local densities or like local functions, then it is clear that the usual algebra of these objects is well captured by the right choices of rewrite rules, right? And particularly convincing, in my opinion, is path integration. I think that's the one that's clearly, it gives you that sense. Now, there's also this notion of homotopy, and you might want to say things like, the curves in your space, they are, the paths in your space, there's a sense of, continuously deforming your paths, right? Like there's a sense in which you can deform a path without breaking it, and that essentially plays nicely with the topology of your space and so on, and that's what it's called homotopy in usual continuous mathematics or continuous geometry or topology. So in this particular case, we might want to be thinking of this kind of rule. We might want to be a bit more stringent and actually consider that there is a full grid of like space stuff. So the undirected edges is the space stuff. The directed edges is the sort of motion stuff. And what this is basically saying is that you can connect 2 to 3, 1 to 2 and 2 to 3, but 2 is connected to 4. Then you should be able to go from 1 to 2, then 2, 4, then back to 2, then to 3. So effectively, you can go from 1 to 4 to 3, right? So that's essentially what a homotopy deformation works. And this particular rule, when applied to, so I think I have a homotopy section here that I can show much more clearly. If you have a spatial graph that looks like this, and I'm interested in the 2 endpoints here, I can think of homotopy equivalent paths that I can traverse this with. So if I take in this graph these 2 things, and I apply the rule of path composition and homotopy deform, right? I can sort of successively apply to say here I'm gonna apply homotopy deform here, and then I'm gonna do path integration. So this kink over here, I'll sort of squash it into this one, and so on, right? And eventually I will be able to deform yellow into red just by applying these two rules. Right? Again, this is a sketch, but in principle it works. So you know that in the future rewriting cone, rather perhaps I should, in the rewriting future cone of this thing with these 2 rules in that rewrite system exists a state where the 2 paths are the same, right? There exist the states in which there's only one path, basically. Right? Like both are sort of rewritten into each other, and they become the same path. So to me, that's a perfectly successful way to encode homotopy equivalence in a discrete setting, right? Again, just with rewriting rules. So it's once again another example of a very fundamental notion in geometry and topology that is purely implemented in terms of setting up your graphs correctly and defining some basic rewrite rules, and then just being clever what to read off of the entire sort of output of running the system, the rewrite system, right? So in this case, you will get, in some sense, a lot of noise. So that's why, this is by no means claiming that we're going to do things more efficiently at first or anything like that. This is just sort of more fundamental statements that we say, hey, if you agree that this is a good model of discrete paths and discrete sort of motion in a finite space, in a discrete space, then we can argue with full rigor that just considering these two rewrite rules is enough to actually encode the phenomenon of homotopy equivalence of two paths, right? And of course, this particular rule is very weak because if I gave something like this will automatically make it equivalent. But we can make it a bit more stringent and consider something like that you can only rewrite two paths, because if you think about this, if there was a path from 1 to 2 to 3, means that there's space from 1 to 2 to 2 to 3, right? And here we are sort of like, this rewrite rule is implying that somehow you could travel from 1 to 4 and 4 to 3. So that is kind of implying that there was space from 1 to 4 and 4 to 3 already, which might not be the case. But if we want to make that more stringent, we just change the rewrite rule and make it more stringent, so stronger, so the application is more strict. And we say, the way to read this diagram is you first assume that 1, 2, 3, 4 are connected in this sort of diamond pattern, right? Where we have 1 is connected to both 1 and 4. So 1 is connected to both 2 and 4, and 2 and 4 are connected to also 3. And then you say, if I have a path that is going from 1 to 2 to 3, then it can also go to 4, that feels more like naturally the homotopy form, where when you have full space in your domain, you can move your curve freely within that domain. So that feels a bit more natural. Again, this is still a sketch because it's not accounting for what is an edge place or a vertex place, but that's basically the idea. So anyway, that's the overall idea. So my two inputs that I wanted for today was ask you guys for your opinion on what is my idea for tensor graphs. So tensor graphs are going to be the higher order extension of vectors. So in geometry, tangent vectors correspond essentially to infinitesimal paths that come out of every point, right? So in some very basic sense, they can be seen as one-dimensional subspaces of the tangent space, right? In other words, a curve is a one-dimensional manifold, right? But if we assume an arbitrarily high dimension for our space, we can have dimension 2 submanifolds, dimension 3 submanifolds, and so on, right? And although it's lesser known and people are not often so familiar with it, there's a similar infinitesimal description of those objects that are usually called multivectors, right? So an infinitesimal oriented surface is a multivector, right? So basically, in the same way that an infinitesimal curve is a vector, an infinitesimal surface is a bivector, and an infinitesimal volume is a trivector, and so on. So what is my idea for those? Well, my idea is that these multivectors should effectively look like, did I run this already? I don't think I did. I need to run this. All right, so I think this should work now. Oops. I have to run it again. The result might not be so pretty. But yeah, so
You can
yeah,
proceed.
exactly.
random seed should be always fixed.
Where's that, Nick?
So you should always fix the random seed. So so like looks nice. It's always gonna look like this.
This is fine. This is good enough. Second try was fine. So at least this way I'm demonstrating that this actually works. It's not just like prepared. So it actually computes the places and so on. Yeah, we should be able to see so that way we can illustrate. This is actually a nice illustration here where you have an edge place down there. So my idea, this is perfect for the illustration I wanted to say. My idea is that for higher order vectors, so for multivectors, what you do is you say, well, how many, okay, let me put this more clearly. When can you say that there is a local surface in a point in space? Basically infinitesimally. That's basically when you can span several points around you, but still don't reach any other point. This is to say that you can extend your arm and point in several directions and basically kind of sweep a surface, right? The moment you can sweep a surface, then that means that there's an infinitesimal surface there. And if you can, if you had like two-dimensional arms, like you could sweep a three-dimensional, with a sheet or something, you can sweep a three-dimensional space and so on. What you need, you need to be able to sweep, right? So in this case, in this tangent space here, in this discrete tangent space that it's currently highlighted in red, you can't sweep your arm, right? Your arm is fixed at pointing in a single edge place that you're connected to. But if we change that to say there, right? We have a pretty central node there, that now you can sweep your arm a lot, right? You can sweep from this one to this one, or from this one to that one, or from this one to that one, right? And you can sweep in pairs, you can sweep in trios, and you can sweep and so on and so on, right? So my idea for multivectors is that in the same way that you are defining your vectors as single pointed edges into edge places from vertex places, bivectors will be directed oriented edges from vertex places to pairs of edge places, right? And so obviously these will only be defined for those vertices where there's more than one edge place. So for example, there we only have vectors, but here we have up to what? 5 vectors, 6 vectors, right? Because we have 1, 2, 3, 4, 5, 6 edges that are incident on the same vertex, right? So, we could the set of all possible bivectors will be all the possible oriented edges. I'm thinking of all possible oriented edges in the same way that when we had the tangent bundle. Let me collapse this. The same way that when we had the tangent bundle, we are thinking of both directions as basically the positive and negative vectors. I am thinking that for multivectors, we should have directed edges just as the vectors are directed. But so you could have any orientations, right? You could have all manner of orientations. So why do I think of this? Let's see if this crashes again. So I'm going to do something. Let's see if I can.
Try killing like the dynamic thing above it. Maybe they.
This?
Yes. Who knows?
Just like that?
Yeah.
Okay. Let me see if this helps. Didn't like it. At least it didn't crash, but it was this case of like. Okay, now it liked it. Right. So this thing. So what does it mean? In this case, I will have from this vertex here. I'll have 2 edge places, the ternary one and a binary one, right? So that means that I can sweep my arm from these two. So why I think this is interesting is that you can start to think to integrate bivectors to generate surfaces. The same way that we thought of integrating curves to, integrating vectors to get curves, now we can think of integrating bivectors to get surfaces. And so if you think of a surface, it should have sort of the simplicial completion, right? Like if there's like an actual surface, like intuitive geometric surface going on between 1, 2, and 3, then surely you should have the sort of full simplicial. Why does it happen? It's not crashing, but it's somehow not liking it. Yeah. So this is probably what a surface looks like, right? Like a triangular surface in geometry. Maybe there should also be some like unaries here. I don't know, for completion or for consistency. But the important, I mean, the unaries are always boring because they are all confined on the nodes. But the point is, if to me this is what a two-dimensional surface looks like. A single ternary edge, although intuitively, visually, one might think, oh yeah, that looks like a surface. I don't think that's a surface because, if you have a surface between three points of space, you clearly have pairwise betweenness between each of the points. Just that's the nature of classical geometry, right? Like if you have 3 points in space, they form a triangle. There is space between any pair. There's no way in which you can have no space between two, but have space between three. Just in classical geometry. So the way that our infrageometry recovers classical geometry in the simplicial sense is by having what I would call simplicial hypergraphs. Hypergraphs essentially that whenever you find an edge of RDM, all the subsets of that edge, the nodes of that edge, will also have edges of all the lower arities, right? So this is such case where 1, 2, 3, I have a ternary edge, and then all the faces of that ternary edge, the two binaries, and then the faces of that the 3 ternaries, right? So to me, this is where that makes sense. And so again, I think we have a nice correspondence. I haven't worked it out yet, but hopefully next week, if we meet again, I'll be able to flesh it out. You can phrase the existence of such things on the basis of having infinitesimal bivector edges that integrate with each other. And the idea, of course, is that you want to somehow probably preserve orientation. And if you're wondering what I'm thinking here, let me see if I can. So I don't know if this will work. Oops. Oh yeah. Yeah, almost done. Yep, okay, that worked. Okay, all good. So basically, if I delete this and you guys follow me with thinking of 5 as the edge place there. Come on. Why? Now, okay. So to me, if I get this kind of pattern here, these are the 2 edge places, right? Like the one in here and the one in the binary and the ternary. So actually, I don't need that one, but whatever. You can say that these 3 things are, these are 2 bivectors. This is just a schematic, but these are 2 bivectors. This is a bivector on this bottom vertex, and this is a bivector on this top vertex here. So if you have this situation, and maybe you want to impose some simplicial ordering here, so the orientations are matching, so that the directions of 4, 5, and 5, 4 are sort of opposite. So you have the usual simplicial sort of contiguous condition. I would say that this, if I find this in my as a distribution of bivectors, of infinitesimal bivectors, discrete bivectors, I would say that this implies that between these two vertices there is a surface, right? Because I drew them. If you delete the things that are in the background, right, where these things came from, and you just show me these two bivectors, what that's telling me is that 4 and 5 are connected. Sorry, 4 and 5 are both directions that you can travel from each of these. So it means that there's at least two things in between, and therefore there's some kind of like surface space or surface-like space between these two things. So again, that would be a notion in which you can be integrating your local structure into that. But anyway, maybe that's enough. We can do some brief comments now and then just move on to the happy hour, not to delay the schedule too much.
Yeah, sorry, I was actually on mute when I just reminded everyone. So for those viewers on the live stream, we are going to be having a happy hour on Discord right after this. So please join us there, and we'll just be able to chat to the community and see some of your faces who would normally just be in chat. Now we can see you on video. That should be cool. This is an exciting progress, Carlos. I think this is definitely seems like there's clear direction here that's looking promising.
Yeah. Any quick comments from Nick or Dugan?
I'm just looking forward to what else it's gonna develop. Yeah, starting good.
Awesome. Okay, great. We'll see you guys in Discord. Okay, bye for now.
See you there.
Bye for now.